Hello everybody and welcome back to this problem solving series on YouTube. So today we're going to be going over vector addition and subtraction, components of a vector, kind of intro to vectors, plus a little bit of some of the operations that you can do to them and how the operations that we're used to thinking about with regular numbers, addition, subtraction, and multiplication by a constant, transfer over to these new mathematical objects. So vectors have a magnitude and a direction, so that can be introduced to you as just the length of the vector and then like wherever it's pointing, the angle with respect to some axes. So that's typically how you're going to be presented with them. So that your initial velocity is 20 meters per second at 45 degrees above the horizontal, go on from there. The other way that you can represent vectors is by components. So if we write them on this XY coordinate grid, then that means that if we have the angle and we have the length, then we could break that down into the X component and the Y component of whatever that vector is. And typically that is going to will have its advantages most of the time in physics, and we do deal with a lot of vectors, so I just wanted to make a standalone video to go over some of these concepts since a lot of you are probably seeing and working with vectors for the first time and they could be a little tricky. There are other types of vector multiplication that's not just multiplying by some constant, by just some number, called the cross product and the dot product. I'm going to save that for a little bit later on. That's just not going to come up for a little bit while, and I don't want to just overcomplicate it, so we'll get to that when we get there. Otherwise, we're going to go to screen record on the iPad and we'll go through how those operators work and also the ways that you're likely to see them, especially in the beginning throughout this mechanics class. Okay, so first thing I want to go over is talking about vector representation the way that I talked about it. So if we have some vector A and we set it up just so that it's at the origin and it has some angle, then, well, first I would say vector has magnitude and direction, where the magnitude will correspond to the length of that vector, and the direction is going to be typically some angle, is a way that you could think about it. Or the other way that we can write it is in terms of components. So say can also write a vector as components along to perpendicular. This definition will become more important as you get into more complicated force setups, but it's two perpendicular axes. It can be more than two. It can be one if you only can move along the X or the Y at a single time. But typically when we think about vectors, we want to think about them in this two-dimensional space. They can also be three, but things get very, very complicated when we get to that, so I'm not even touching that yet. So we're just working with two. And we are also only at first going to be thinking of our axes as X and Y. So like I said, we can do more complicated things, but we can also write this AY as a component of A that lies along the x-axis and a component of A that lies along the y-axis, or AX and AY. Now, you can also draw these. So you can move the vector position depending on where it's convenient. So we'll talk about that a little bit more in addition. But even for this, so one of the things that we can do is we can move That's so annoying. Okay, let me draw it over here. So AY is just 2 up. It's roughly how I drew it. And we can really pick where, we can draw it from this end, which clearly I drew it a little short there. Or if we draw it here, then we can start to see the connection more clearly between vectors and then our right triangles, which is why we talk so much about SOHCAHTOA and our trig functions and Pythagorean theorem, and that's stressed so highly in the first video. Because when we add, so first I'll say, so obviously in physics we're using a lot of equations which involve addition, subtraction, multiplication, division, so on and so forth. But now instead of having regular numbers, which we all know the rules are, we've been learning that since first grade, now we're having equations with vectors, and they have different rules. So, addition and subtraction. For vectors, they're going to add component-wise. So if we have vector A and vector B, which we'll call some new vector C, and this is just the definition. So if you ever see 3 lines on the equation symbol instead of 2, that means it's being defined. So we're going to define some new vector C that's equal to vector A plus vector B. And how you would actually do that is you would say, okay, AX plus BX is equal to CX, and AY plus BY is equal to CY. Then, if you actually, most of the time, they're going to ask for whatever this new magnitude is. Once you have components, well, I'm getting a little bit ahead of myself. Okay, stop here for a second. Let's go back to connecting the vectors to the triangles. I glossed over that a little bit more than I wanted to. So, SOHCAHTOA. This is why it's going to come in handy depending on what you have. So you need to have at least 2 of these things, the magnitude and the angle, AX and AY, or any other combination of 2 out of these 4. And then with our angle defined there, we can say sine theta is AY over A. We can say cosine theta is AX over A. Tan theta is AY over AX. And can I squeeze this in here? The magnitude of A squared is equal to AX squared plus AY squared. So now once we have that, let's hop back down to equations, or the addition and subtraction, I guess I should say. So this is how you would add to get the components of CX. And once you had those 2 components, then you could get the magnitude by using Pythagorean theorem for the C vector, whatever that guy is, and you could get the theta from doing CY over CX and then taking the inverse tangent. So before moving on to subtraction, let's also look at this example and show some actual arrows, and again, like how I want you guys to be able to put these together. Before we get into subtraction or the other operations that I wanted to talk about, I first want to show you what I was talking about with drawing. So if we do have 2 vectors acting on something, so this is our point, and say we have A going this way and B going this way, then you can kind of see, but it's not always so easy to see, that the resulting vector C is going to be somewhere in this area. But what makes it a little bit easier to see, so let's see if I can draw this B parallel. Try one more time. It's more like that. I think even that's too short. That's okay. I'm sure you get my point. So what we can do instead is you want to line them up tip to tail. And so I got the size of C way off, but it is actually like roughly along that dimension. And then, so I'm going to draw it both ways. So that way you can just see both ways and how they're drawn both ways and how they get connected. So I'm going to do A as 3 like that. And I'm going to do B like this. So let's do stuff that's easy. And then right there, Y components. And the X components, AX, BX. And then I'll leave that picture like that, and then I'll draw the other one. So from the other one, we have A, 3 and 2, and B, we want tip to tail, so we're going to go here, so we're going to go down. The resulting vector C goes from the tip of the last vector you're adding to the beginning of your starting vector. So this is going to be C. And so part of the reason why I don't like to draw it this way, at least not for this example, I chose kind of a bad example, but I'll try and draw in some different colors here so that way hopefully you can see what I'm talking about. But with the numbers, so I'll do A in red. We had 3 going across, and we had 2 going up. And for B, which I'll do in green, we had 2 going back, and we had 2 going down. So that ended up leaving us with C had no component in Y at all because these guys completely canceled each other out. Oh, C was dark blue. And then if you add these guys, all that's left is going to be this little bit of CX, which ends up being all of C. If you do, so these pictures just get a little bit difficult with drawing arrows, but I think once you get over the fact that the arrows have to be where like connected to the triangle so that they all get kind of mixed up, then that can make things a little difficult, but you can also spread it out like in that first way I drew it. Then it's just a little bit harder to see exactly the direction. It's not as intuitive to see the direction that the C vector is going to be in, but once you have the components, you don't necessarily need to anyway. So now we're going to have instead A minus B is going to be defined as our C. And the rules still apply that it's going to happen, the subtraction is going to happen component-wise. So, but now we're just going to distribute that minus sign to the B values since we're subtracting now. A y minus by equals cy. All this stuff that I wrote up here is the same if you have numbers. And I guess I'll also make a side note. It's very common for them to give you the magnitude and directions of A and B, so that way you have to get them into. It's very common in general for you to start with a vector or start with magnitude and direction, break into components, and then go back to recombine, I guess I'll call it, to magnitude and direction. So, and in between, in this stage, there's some sort of addition, subtraction, etc. happening but just as kind of a side note for how these problems, how they add in complexity. We always want to look for them adding in complexity. But, so how this is going to look for these vectors. So again, we have A is going to go 3 across and 2 up. B is 2 across, 2 down, going to the left. So what you can do is you can either think about subtraction as now instead of lining them up tip to tail, you're going to line them up tip to tip. But I think that the easier way to think about it is instead to, what you can do is if you think of a negative b, and like I said for the actual operation itself, that's going to distribute itself to each of those. So you can instead think of this as adding a negative, and all that would happen here is that our bx component and our by component, everything's going to flip. So let me actually color code this a different way. So if we're going to go negative, then bx is going to become negative bx. So this arrow is going to switch direction. And by is going to become negative by. So this guy is going to switch direction. Overall, this leads to our negative b switching direction. And then you can go ahead and just add tip to tail the way that you normally would. So now I chose my A in a bad spot to be able to do this. So I'm going to move that arrow over here. Then we'll add the negative b. And I guess what I could also show, if I can isolate this, is if you were to line them up tip to tip instead of tip to tail for subtraction, you would do the same. You would end up getting the same resulting vector because the resulting vector is still going to go from there to there. Ooh, okay, my negative, there we go. My other b lives there forever now. And then I'll still show a navy blue, but the picture is going to get pretty busy because of the vectors that I chose, but C is going to look like this. We still have our AX. Now we have our negative BX, and we have AY, and BY, and then the other thing I'm just going to show here, since this is a nicer picture to see it, is that we have CY and we have CX here. So that kind of also just shows adding these together will give you those, adding these guys together will give you that CY. Okay, last step, which I think I've already spoiled the punchline that I wanted to talk about here, was multiplying by a constant. So, which is kind of what I did with that negative as far as the subtraction. So multiplying by a constant, it just distributes. So if we have, I guess I'll stick with C, is going to be defined as some constant. No, I don't want to use that. Let's use something different. Some constant K. So this is just any number that's not a vector. Any scalar quantity times A is going to distribute so that the magnitude, or C, actually I think the magnitudes do scale, but let's just think about it component-wise. CY is going to be that constant times AY. CX is going to be that constant times AX. And then let me quickly check myself. So if C squared is CX squared plus CY squared, then that's going to be equal to K AX squared, or K squared AX squared, K squared AY squared. You could pull out a K squared times AX squared plus AY squared, and if you take the square root, you get C squared equals K times, so this would also just be the magnitude of A. So actually I'm not going to. Sorry, if you take the square root of that guy, that is the same thing as the magnitude of A. So yeah, and the squared is supposed to go away. So that constant will scale the magnitude the same way that it scales the component, so it just multiplies. So yeah, so the only thing else that I would say, just putting it all together, so the last stage would be if you had a problem that did all of these things. So if we had 3a plus 4b is going to be c, and we just want to know cx and cy in terms of ax and ax, ay, bx, by, we would have 3ax plus 4by equals c, oh my gosh, x. X's, 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 y's, y's, y's. And we would have 3ay plus 4by goes with cy. Vectors are all over physics, so it's not even like it would be easier for me to give you a list of where you're not going to encounter vectors than where you are. But for the beginning part of this class, if you are watching this video a little bit later, you might have seen this in projectiles. And vectors start to get introduced there, and the idea of working along components because you're given equations that work in y and x. But I don't think, not all the teachers explicitly say that you're working with vectors necessarily. Not in the same way that it happens when you start to talk about forces. Forces and vectors typically are much more likely to go hand in hand with one another. So forces, adding forces together, forces interacting with each other, momentum, accelerations, velocities, positions, these are all vectors, and we've already been dealing with a lot of equations with vectors. So when adding vectors together, just keep in mind we want to add component-wise. That's the number one thing. And if you remember to add component-wise, that the constants will distribute to each component, your SOHCAHTOA and your Pythagorean theorem, then you can handle vectors. It's 4 things. You just need to know 4 things. And you got it. Vectors are done. So thank you guys for watching this video. The next one that should be out is going to be all about forces. So looking forward to that. Speaking of which, we'll go to a clip of Howitzer for our outro, and happy physicsing. Bye guys.
What are you doing? Are you acting crazy? Are you acting crazy? Can you sit? Sit. Good. Paw. Good boy. Okay, you can have your bone.